once we talked about the max heapification procedure, it's better now to talk about the build max heap procedure. Okay, so build max heap is the another operation on the heap data structure, and this is about from an unordered array how we can reach to um, a heap data structure or a heap verification tree, you can say. Okay, so the build max heap, this is the pseudocode for the build max heap. What does it do? It converts a 1 to n an unordered array to a max heap. Okay, so this is the pseudocode build max heap. When the array A is the input, for I equal to n by 2 down to 1, do max heapify AI. Okay, so see, that's why we needed to learn max heapify before build max heap, because build max heap is actually calling the max heapify. That means correct every violation one by one stage at a time. But the concern here is that, or you can say the query is that I equal to n by 2 down to 1. So now here I want to say that this n by 2 and all this, the I, the A, this is the index of an array. Consider this is a okay, heap data structure, and this is the array. Okay, there's the input array A. Okay, so this is an input array, and this is the index. Okay, 1 2 3 4. Now when I equal to n by 2 down to 1, why n by 2? This is a concern. Okay, why we want to do from n by 2 and not from n to 1? Okay, so so the reason is that the half of the node, the remaining half of the node, are actually at the leaf level. Okay, we shown that in a previous video. The remaining, the half of the input array A is at the leaf level, so they are basically the the max heap, trivial max heap. Okay, because they do not have any children, so there is nothing to max heapify there. So they are the trivially satisfying max heap. So we can just forget them. Even if you do from n, the complexity will not decrease, you can say. So this is a better to do from n by 2. I mean, you can do from n to 1, but the last half will not be actually utilized. There's nothing to do. Okay, so it will just recur. So we want a better algorithm with a more tighter bound. So we do from n by 2. So n by 2 for this 10 elements, n by 2 will be from 5. So from 5 we go back this way. Okay, 5 4 3 2 1, and that way. And then we run max heapify on every element. Whenever we see there is a violation, we keep running that. Okay, so we are actually, if you say 5 4 3 2 1, we are actually going from lower to higher. Okay, so what will be the complexity runtime of this algorithm? So this is, suppose this is running n times. This is actually n by 2 times, and this max heapify we have already shown that it's actually it's order of log n. Okay, so if you can kind of multiply this two for the, because there's a for loop, so this actually should run n by 2 times log n. Okay, so this will be like order of n log n. Okay, so n times you keep checking, n times you do max heapification. Every max heapification takes log n time, so it's n times log n, simple multiplication. Okay, so this is a correct one. This is the correct complexity time taken by the build max heap algorithm. But this is not a tight bound. Correct, but not tight. Okay, so this is correct, but not tight. Okay, so n times log n operation, so n times log n. So, but this is not tight, because we can see that as I said, for the lowest level of the leaves, they are already root of the trivial max heap. So we do not need to do anything for this node. Suppose there are 2 to the power 0 number of nodes, 2 to the power 1 number of nodes, 2 to the power 2 number of nodes, 2 to the power 3 number of nodes. So this is actually here, if there are 15 nodes in this tree, so there's 8 nodes, like 15, this is like almost half of the nodes, n by 2 nodes at the leaf level. That's why we do from the upper level. Okay, for the upper level nodes, if we start from this level, you can see that the max heapification actually have to run just for one time, not log n time, just for one time. Suppose this is having problem and this you need to exchange with this. That's all, one step, okay, because this is just above the leaf level. So at this level, max heapification will take like order of one time. Okay, max heapification will take order of one time. What about this level? If you do this level, any violation, suppose this and then this, so this might take at most order of 2 time. Okay, so we are trying to get a tighter bound. In that way, you go on. Okay, suppose there's a longer tree, more the height is bigger, and so at this level, the height of a binary tree we know it's a log n. So this at this level, there'll be one node which will take log n times here to here, here to here, then here to here, maximum height of the tree. It might go on for max heapification with those exchanges to correct the violations. So this is as a log n is the height of the tree. Now what we are trying to say, there are n by 2 nodes at leaf level. Okay, so we do not need to do anything. So they actually cost nothing. So we just forget them because that's where we start from, one level above the leaf. So then there are actually n by 4 nodes. You can see there are like 4 nodes out of 15. So n by 4 nodes at this level. Level 1, we can say this is level 1. Okay, now this one level we are considering from the leaf. So now n by 8 nodes. So every time you go upper and upper in the pyramid, the number of nodes at this level are reducing. Okay, so n by 4 nodes at leaf level, n by 8 nodes at level 2. Sorry, n by 4 nodes at level 1, n by 8 nodes at level 2. Okay, in that way, there's one node in the log n level above the root. Okay, log n, one root node at the log n level. So how many times this for loop is running then? N by 4 times it will run when this is constant order of 1. Okay, one maximum 1 exchange. So what about this? N by 8 times 2 order of 2. So it's you are a constant, and in that way you will go on until the log n height, where also constant cost just for one node. Okay, one node at the log n level. N by 4 node at this level 1, n by 8 nodes at this level, n by 16 nodes at the third level. In that way, the maximum 3 number of exchanges. So if we sum it up, if we can take out to the power k as n by 4, and then it will be represented using this series, and it is so finally when this because this is actually a linear function of n, so because n by 4 is being represented to the power k. So when we sum it up, this actually becomes order of n. Okay, so what does it mean? It means that although the build max heap upper bound is actually order of n log n, a very tighter upper bound is order of n. Okay, it's you can say this is a tighter upper bound, tighter bound for build max heap is order of n. So that's a linear time. Okay, so that is actually a very efficient algorithm because it can operate in linear time. Now let's see an example. I've already shown you this array, and I said that from the n by 2 down to 1, the for loop will recur and keep correcting the violations using the max heapification algorithm, which takes like order of log n time. Okay, so now I have tried to represent this same array using this tree structure. If you see root is 4, then position of root is 1. 1 times 2 is the second element is the left child, the third element is the right child, and then again in that way, following that left root right is I plus 2i plus 1. In that way, I have represented that, and now you can see that this is we have to do the max simplification. So we will consider that from this node, and we consider that the left child initially, the left subtree is a max heap, and we are trying to correct the violation at this node. And then we see for max heapification, we will call on this node A5. You see max heapify from down to 1, we are going backside from first to on the 5. Okay, so there is no change because this is already a max heap. Okay, 16 is more than 7, so there is only one child. Now the for loop continues. This is the second step. Okay, this is, you can say, the first step. This is the second step. Max even A4. Okay, I is going down. So A4. So this is this node now, which is 2. So what we do, swap A4 and A8. Okay, so why we do that? Because this is violating max heap property. So initially we consider this left subtree is a max heap, right subtree is a max heap. That is true because you know that they are leaf nodes and they are max heaps of their trivial no child tree. So now we are trying to run max heap on this node, and we are seeing, okay, among them the largest is 14. So we change 2 with 14. Okay, 14 here and 2 here. So see, that was the swap A4 and A8, the positions 4 and 8. Now that is done. This is now a max heap. Now we go from index number 4 to index number 3. Okay, so this is the step 3, index number 3, and element is also 3. So everything is 3. So now at this stage, swap A3, we are considering this and this are max heaps, trivial max heaps, and then the root, we run the maxify on the root of that, and we find that among this 3, 10 is the largest. So we swap A3 with A7. You see, we swap A3 with A7. So this one becomes 3 and that will become 10. So this is 3, this is 10. Okay. Okay. Now you see what we do. We go for from 3 to 2. Okay. So 2 we again consider this is a max heap. The left and right children, they are actually max heaps, and then we run the maxify on the root of this whole subtree, and that is maxify on A2. That is the item number 2. That is the step 4. And what we do, we check among these 2 which one is highest. We see that 16 is highest. Okay, so we swap A2 with A5. You see, swap A2 with A5. So this one becomes 16. This one becomes 1. Okay, this becomes 16. So now we have to check whether the property, the maxification, will go on till the leaf level, if you remember. So now we have to check in this subtree, is there any violation? I see yes, this is a violation because this is now smaller than the child. So 7 will go up and 1 will come down. So A5 and A10 we swap. You see, that's A5 and A10. So this one becomes 7 and this one becomes 1. Okay. So now this is correct. We are at the leaf level. 1 has no problem. It's a trivial max heap. Then we go I reduce by 1 and go to the index value number 1, which is item 4. And so that is the A. We run maxify on A1. That is the this step. Now at this step, what we do, we find out that this is 4, which is not the maximum of their children. So now we have to see which one is the largest. We find A2 is the largest, which is 16. So we swap A1 and A2. You see, A1 and A2 we swap. So this becomes 16, this becomes 4. So this becomes 16 and this becomes 4. Okay. Now you see, we check that 4 is actually again violating the max heap property. So among them, this is the highest. So we change A2 and A4. Okay. So A2 and A4 we swap. So you see, this one will become 14 and this will become 4. Okay. So now this again, this 4 is violating max heap property. So what we do, we swap with the largest, which is 9, A9 with A4. Okay, A4 and A9 we swap. So this becomes 4 and this becomes 8. So now there is no more violation, and now this heap is a max heap. So from this unordered array, we changed it to a max heap. Now you see the maximum element is at the root node, and this is the explanation of the build max heap property and the analysis, tighter complexity analysis and the loose complexity analysis of the build max heap procedure for HeapSort. Now, once we have already discussed the max heapify and build max heap operations on the heap data structure, we are ready to discuss the HeapSort. Okay, HeapSort algorithm. Now it actually becomes very simplistic because we already discussed the the main operation. So what we do, we follow the same example as earlier, and now this is the kind of a step-by-step operation of the HeapSort algorithm. So it says that initially build max heap from unordered array. Okay, so we have already built a max heap from an unordered array, and there is a heap size was you can say this is the heap size. Heap size was initially all the 10 elements. Okay, heap size equal to 10. Assume that heap size is actually the size of the array. Okay, the whole array we are trying to convert into a heap. Okay, so we build max heap from the unordered array. We have shown how to build max heap using the max heapification procedure, which involves a swap operation. Okay, so now we find the maximum element A1. As we know, it's a max heap, so the maximum element will definitely be A1. Okay, so this is the max element. Now what we do, now swap element AN with A1. Okay, so AN means here nth element is the 7, that is the 10th element. So we swap 16 and 1. So I change it to 1 and then change it to 16. Okay, now this is not max anymore. Okay, so now max element is at the end of the array. This is the max element now, 16. What we do now, we say discard node n from heap. We discard node n by decrementing the heap size variable. We don't need to do anything actually. Okay, we just leave 16 there at this position and change the heap size to point to here. And now the heap size is actually, instead of 10, this is 9. So 16 will be here and the remaining element will be here. This is not max anymore after the swap. So if new root may violate max heap property, but its children are max heaps. That was the definition of the max heapification. If you remember that this left child is a max heap, right child is a max heap, but the root node is not a max heap. Root node is violating the max heap property. So what we do, we max heapify again until this is again a max heap. Okay, so you assume that this is gone, so this node is not there anymore. So this is actually this is not there anymore. Okay, in the heap, so this is out. So in that way, again we do max heapification. You know the procedure. Then what will happen? The next maximum element, which is 14, will go here. Okay, so when 14 goes here, so then again what you do, swap with that. So if just let me do one step. So this is 1 here. So this is maximum of this. We'll pick up 14 and put the 1 here. Okay, swap with 1 and 2. And then now with this 1, this is violating the property. So 8 is max. We take 8 up here. Okay, then this is also violating. So maximum is 4. So we take 4 here and 1 comes down. Okay, then what we do, we again swap 14 with 1. So again this becomes 1, 14 comes here. Then decrease the heap size again by 1, and then 14 comes out of the heap. Okay, so again you keep doing the same thing until all the elements have been found, and you can see that now they are forming a sorted order. Okay, so 16 and 14, and then I think it will come, then 10 will come. In that way, we will continue, and this is the HeapSort procedure. So at the end, you'll find the sorted sequence, and so this is actually the heapification is running in log n times, and on the n elements of the array. So the running time is Tn of the HeapSort is Tn equal to order of n log n. Okay, so on n elements you keep doing the heapification again and again, and heapification takes log n time. the total running cost is order of n log n for HeapSort. Once we talked about the heap data structure and all its operations like build max heap, max heapification and stuff like that, we will talk about one data structure which is a direct fallout from the heaps. Okay, so it's called a priority queue. What is a priority queue? It's a data structure implementing a set S of elements, each associated with a key, okay, supporting the following operations. What are the operations? Insert SX. So what does it do? It inserts element X into set S, okay. Then we can do max S, okay, maximum element of a of this array S we can find out. So that's the element with the largest key. So now try to consider parallelly this example where at the you run HeapSort on an unordered array, and then you can generate the maximum element which will come to the root of the array. So priority queue implementation is based on a binary heap data structure. Okay, without a heap you cannot have a priority queue implementation. So the lower level of the priority queue is actually the heap implementation. So every time you run max, you do the max heapification and pick out the root. Okay, if it's a min, if it's also possible to have a minimum element, then you do the min heapification and pick out the minimum element. Okay, so it's a minimum priority queue, and this is like a maximum priority queue. So extract max, what does extract max does? It returns the maximum element and then removes it from the array. It's very much like this. Okay, what we did in HeapSort, we returned the max element in the root by max heapification, and then we pick that and take it out of the array. So by reducing the heap size variable by 1. Okay, so that is this operation. So that operation we needed to implement this extract max. Okay, this is extracting that maximum element. And the last is the increase key. Okay, so increase the value of an element XS key to a new value. Suppose now the value of 1, I want to change it with like 5. So I can do that. Okay, I need to find that element. Suppose we pick out the minimum or the maximum element of the heap and then change the value to certain other value. Okay, so this this insertion, as I already said, insert into the data structure, and all this operations are actually based on the heap binary heap data structure. So priority queue will be necessary for dealing with multiple algorithms at a later stage, like Prim's algorithm of minimum spanning tree uses priority queue, where multiple graphs have different distance estimates. Initially all those estimates are infinity. So okay, so there will be all the elements in the array will be infinity except one element, which is distance estimate is 0. Distance estimate, actually we say when we talk about Dijkstra's shortest path algorithm, for minimum spanning tree we say that the weight of the vertex estimate, and then the minimum element we always pick. Okay, then we change this infinity from this node, the minimum, suppose this is another node, and if there's the edge connecting it have a weight of 5, so we change this infinity to 5. Okay, so in that way this is this increase key or decrease key, this kind of operation. Okay, so it's an implicit operation. You can increase, you can also decrease. Okay, decrease key is also there, decrease key. So this is just a complementary to that. And for this max, there is a min operation also. You just need a minimum priority queue. Okay, so this kind of operations are important, and we'll be using them at a later stage for different other algorithms.